Okay, what have we seen some hours ago? We have seen a theorem that relates the expectation of a function of a random variable with the integral of the function with the distribution of the random variable. Then we saw some examples of expectations and some inequalities. So let's continue from the point in which we left. And let's start with a lemma, which is about the integrability of a random variable. So a random variable x is integrable if and only if we have the following situation: the limit for b going to infinity of the expectation of the absolute value of the random variable restricted on the interval in which it is larger than b. This thing goes to 0. And this result will be used to check the integrability of a family of random variables. So what happens here is that we consider the right tail of the random variable. Let's say it's an exponential negative, and we have some boundary b, and we just consider the positive part of x. So maybe if it is something like this, we just consider it in absolute value. And this thing here is simply that means simply that we consider the random variable if this is x, or x in absolute value if you want. This part here is this part, this thing. So when the absolute values, when the values of x are larger than b, we only consider the right tail. And if the limit of the expectation, which means the limit of the integral, this thing here, goes to 0, it means that the random variable is integrable, so it doesn't explode, basically. And for the proof of this, call zb the absolute value of x restricted on the values larger than b. And notice that this is less than x in absolute value. Why? And what do we actually mean by this? Because here they are the same, basically. If I understand well, what we mean by this here is that for the same values of the domain of both random variables, so this variable is defined on the domain b plus infinity, while the other one is, let's say, from R in R plus, and on the same domain, this is larger than this one. and this thing goes to 0, well, and ZB goes to 0 as B goes to infinity, by assumption, right? I don't understand this part very well. Well, this is because x is integrable. So also z is also integrable. Okay. And to be integrable means that it must go to 0 as b goes to infinity. Okay. Now, since x integrable, we can apply the dominated convergence theorem to say that the limit as b goes to infinity of the expectation is the expectation of the limit why is this 0? Because this thing goes to 0. All this goes to 0, so the expectation of this goes to 0, I think. I don't know why we actually call ZB if we keep using this in the proof here, but so this implication is proven. Now for the other one, if the expectation of ZB is 0, we have to prove that x is integrable. Well, this goes to 0. We can choose B. B such that there was a 1 involved here. The expectation of ZB is bounded by 1. Why? So if this integral goes to 0, we can choose a value for b which is smaller, so that the integral is 1 or less than 1. And this implies that, and we know here, okay, and we know x is zb plus b. Why? No, no, no. It's the x is bounded above by this. Why? How can we relate it here? What is zb plus b? In any case, this implies that the expectation is less than the expectation of zb plus 1. No, plus b. Plus b, which is bounded by 1 plus b. And this proves that this is finite. So it's integrable. Not everything is clear, probably. And I will have to review this again. So what are we doing here? We have a condition to check the integrability of a random variable by looking at the right tail. If the integral of the right tail goes to 0, the entire random variable is integrable. So, which means the integral of the entire random variable is 0. And one question that I had is, what if the random variable explodes, like for example here, before b? Anyway, let's leave it here and give the definition of uniformly integrable random variable. Well, actually, uniformly integrable collection of random variables. So, well, let's just write a collection k, script k is integrable if and only if, well, here it gives just an if, but I think it's if and only if. Well, it's a definition, so if k of p, which is this thing here, limit as p goes to infinity of the supremum over dx in k in this family of the expectation goes to 0. So we consider the largest random variable among the collection. If the largest random variable among the collection is integrable, then the entire collection is integrable. This should be the meaning, I think. Now here we have some remarks. So if k is finite, if k finite, and each x is integrable, then the collection is integrable. Is actually uniformly integrable. Another remark, if the collection k is dominated by an integrable random variable z, then, or actually uniformly integrable, no, just integrable, then k is uniformly integrable. And here another remark which is very important is that uniform integrability implies L1 boundedness. And let's give an example. Well, this means that k is in L1 and k of 0 is the supremum over k of the expectation of x is finite. I don't know why this is called k of 0. It may be like this, but 0 here doesn't make any sense. Why k of 0? Well, let's continue with the proof, well, or the example if you want. Or this is actually, well, here it is given as a proof. So the expectation of the absolute value of x is bounded by b plus k of b. Always true for any x in k. Since each random variable is in k and k is uniformly integrable, we use the uniform integrability of k to choose a value for b such that k of b is less than 1. So you can construct a further bound for that b. What does it mean? I mean, we act here and we will bound this again by something, I think. And prove this thing. Let's hide this thing here. What happens if I do this? Okay. And if I do this? Okay, no problem. For all of them. Then take the larger b and you have actually proven L1 boundedness. So we have proven that the expectation of x is bounded by some b plus k of b, which means we gave a uniform bound for all the random variables in the collection. And then by uniform integrability we give a uniform number. So we have bounded expectations for all the random variables composing the collection. Therefore, the supremum over k of the expectation of x is bounded. I will have to review this proof also. As the next thing, we will see next time that L1 boundedness does not imply uniform integrability.